Hi there. In this video, let's learn a Linux kernel module. It's been a long time since I did programs on Linux kernel module. Here I've seen me by one of my old videos has been almost like 10 years old. All right, so we'll learn how to interface a file in proc file system on Linux kernel. Well, if you have worked on Linux, one of the interesting things that you'll see about a Linux system is the existence of /proc, which is not unique to Linux, but I believe that Linux has sort of improvised or evolved to expose a lot of statistical details via files and folders under /proc. You'll see a lot of files in here, and if you go to /proc, you'll find files to represent what was the command line argument that was used to boot the kernel parameters. You can find out what's the version of the kernel that's currently running. You can also find out a lot of statistical details like the CPU information, or you could also find out information about memory. Now, if at all I want to write my own module to add a new file in here to expose some statistical details, how do I do that? So we'll find the easiest way to solve this. One of the ways is to go through documentation and try to figure it out, but I'll tell you how to get surviving on the Linux kernel development. So if you're already using a kernel, you can download the source code of the Linux kernel from kernel.org. There are two ways to get the source code. One option is to actually use the Git repository, which is what I've done. But if you do not have enough disk space and you want to get onto speed very quickly, you can download the latest kernel source code from here. This is a tarball. You just download this tarball, untar it in a folder. But what I've done here is that I've synchronized my kernel with the Git repository, so I can switch across different versions, and I can also look at changes that have been happening across different versions. So it makes me manage things better. So if you're into kernel development, I believe that having a Git repository might be very, very useful, especially if you understand the history of how certain functions evolved in the kernel. But if you're under speed, you can also untar a tarball that you download from here. As you can also see that the latest kernel is 6.0, which is right now transitioning as a stable kernel. It's a stable release right now. So the earliest stable release is 5.19. So you'll find many Linux distributions still using 5.19, any of the rolling distributions. A couple of stable distributions would be using 5.15 series of kernel. So to find out what version of kernel I'm using on my system, which is an Ubuntu based build, you can run a command called uname-r. You can run this command on your system too to find out the latest stable, what version of kernel your system is currently using. So the kernel running on my system is based on 5.15. But having said that, I have synchronized the kernel source tree in this particular folder, Linux stable. Basically, the stable tree is what I've synchronized. It's a kernel source code, which I assume is a kernel source code that's just untarred in here. When you untar a kernel source, you'll find all these folders. To know more about files and entries that go into /proc, you might want to look up FS. FS stands for file system. All the file system related code will be in here. VFS layer and all file system drivers and their related code base you'll find in this directory tree. Under FS folder, you just go to /proc, fs/proc. You'll find the implementation of proc file system. But without having to worry about all the implementation details, I can show you some interesting files in here which map to entries that you see in /proc. For example, if you look at /proc's version, /proc/ uptime, /proc/ loadavg. All of these files exist in /proc. The actual source code for exposing these files are in here in the kernel source directory under fs/proc/version.c, fs/proc/uptime.c. But I've actually run ls command here. You can see that, right? You can see a file called uptime.c. You can see a file called version.c. You can also see a file which is called loadavg.c. You can also look up files like kmsh, meminfo. So all these expose all the simple files that you see in /proc. If you know how these files are implemented, it should be not very difficult for implementing one on our own. What we'll do right now in this small exercise in this video is to expose one kernel variable called jiffies. Jiffies is a variable that is updated based on the timer tick. The Linux kernel has lots of timers, and there's one timer chip that's armed to take care of preemptive scheduling, right? So this timer callback handler is generally schedule underscore tick, and this particular function will basically figure out when schedule must be invoked and so on. So basically the granularity of this timer tick varies from 100 Hertz to 1000 Hertz based on the kernel build. And at the rate of that particular timer tick, jiffies variable is updated. So the jiffies can be used within the kernel for very basic instrumentation at the granularity of, let's say, milliseconds. So if at all I want to find out how many milliseconds does it take to run some function, I can actually use start is equal to get jiffies 64 and then perform some activity. Then I can just say duration is equal to get jiffies 64 minus start. So I can actually use this particular technique. Now, this jiffies variable is defined in include Linux jiffies.h. I just want to expose the value of this variable. Though you could access the variable directly, it is suggested not to do so because of a lot of synchronization related issues. So there's a safety scaffolding function that is to be used to access this variable. As you can see in the source code, you can see that this is the variable jiffies64. But there's a nice comment on top. It says it's a 64-bit value which is not atomic. You must not read it without sampling the sequence number in jiffies lock. The safer way to access it is by using this particular function called getjiffies64, right? So let's try to use this. I want to call this function, get the value of jiffies and expose it as a file in /proc. So how do I do that? Well, let's try to expose this file by creating a folder. I'm going to create a new folder in here. I have my own directory. Don't worry about the file here. I'll explain about this file in a while. I'm just going to create a folder called proc_jiffies. This is an empty folder. All I'm going to do is I'm just going to copy one of the files which implements /proc version or uptime. I'll select /proc version. I believe that's the more simplest because this particular variable, this must be coming from some variable, right? So, or a bunch of variables, let's say. This is what is printed. So the version of Linux and the build and other details. So if I know how version.c is implemented, it's not very difficult for me to expose jiffies. So let me copy this file. I'm just going to copy user local src Linux stable, basically the Linux source code, untagged Linux source code in this folder. Under that fs/proc/version.c, I'm going to copy that as proc_jiffies.c. Now I'm just going to open this file, procfs.c, and I'm using Vim editor, by the way. I'm using NeoVim. You can use any editor of your choice, whichever editor you find comfortable to use. So here, the word called version, I'm going to just change it to jiffies. So I'll just say percentages, all occurrence of version. I'm going to change to jiffies globally. Convenient. Now, one of the aspects about many of the files that you find under fs/proc folder, fs/proc folder in the Linux kernel source code, the files they actually expose, they're all built-in modules. Built-in modules cannot be unloaded. So when you boot your Linux system, you don't have an option to say expose version or not expose version. It'll always be there. So because these are built-in modules, their entry point functions are registered using built-in helpers like fs init call. Sometimes you'll find device init call, subsys init call, and so on. So we're going to make this change because we're going to be building an out-of-tree module. So because we're building an out-of-tree module, the module that is not part of the kernel source tree, we might need to have a proper module initialization and cleanup semantics. You can look up my earlier video, a very old video, in fact, it's close to 10-year-old, but the concepts are still relevant even today about loadable kernel modules to know more about module init, module exit kind of macros, right? The module entry point and exit routines. But now I'm going to make some changes to support that. First of all, I don't think I'll need this SPDX license identifier because this is not going to be part of the kernel source tree. It is going to be an out-of-tree module. So I'm going to delete this line. It's just a customary comment to indicate what kind of licensing is supposed to be followed. We're going to use our own license, maybe GPL license, right? We're going to put that below. And because this is going to be built as a loadable kernel module, all loadable kernel modules will start with a linux/module.h include. And I'd like to put this kernel.h below here. These are like the two standard header files that you normally include for most of your kernel modules, right? Whether it's loadable kernel modules or even built-in modules. I believe I don't need init.h because init.h is included through kernel.h. So I'm going to remove that. I don't think I'll also need fs.h in this case because procfs.h and seq file.h internally includes fs.h. So I'm going to remove them all. I don't need uts name.h because this is required for exposing features like the name of the system, the kernel release, and other details. So I'm just going to remove that too. And then what I'll do here is, if you look at this particular line here, it's fs init call, it says proc jiffies init. That means when a module is being loaded, you're supposed to invoke this function. This function is registered as a callback handler to be called during initialization. I'm going to change this fs init call to module underscore init this time because this is going to be a loadable kernel module. So let's make this change. We just say module init of jiffies proc jiffies init, and I need to be able to unload this module too. For that, I'm going to register another function, module exit of proc jiffies cleanup. Basically, when I unload a module, whatever entry that gets created by a proc create single, that must be undone. This proc create single is a very high level API which is used for exposing a file in /proc in a modern kernel. There used to be functions like proc underscore create, proc create data, and create proc read entry in the early versions of Linux kernel. A lot of them have been deprecated. Some of them are low level functions, very rarely used, but for most purposes you should be just using proc underscore create underscore single, and the first argument to that is the name of the file that you want to expose. This will be the name of the file that will be shown up in /proc, and the next parameter indicates the permissions. The 0 here indicates use default permissions, right, which would indicate read for user, read for group, read for others, read permission for all three domains, I would say. And this third entry is supposed to be under which folder to add this file. This must be an instance of a proc directory structure. If you happen to create your own directory under /proc by using proc mkdir API, the return value of proc mkdir will return a proc directory pointer, and that can be passed as an argument in here. Otherwise, you can just leave it to null if you want to expose this file in the top level directory. The last parameter, what you see here, is what is important. This is supposed to indicate the callback handler that will be invoked when a code in user space tries to read from this file. Normally, to access a file, you open a file, you read, and you close it. The open and close callback handler, you don't have to worry about this. The proc create single will create a boilerplate for it, and then whenever you try to read from the file, the show function is called. This proc create single is a very high level wrapper on sequence file API, which is a common framework for exposing pseudo files to user space from within the kernel. Then there are two variants of it. We have sequence create and sequence create single. Basically, it's called sequence open and single underscore open. Single underscore open. This proc create single actually means that once you open the file, you can just read once. You cannot read another time. If you try reading another time, it will return end of file, which is empty data. So you can open a file, just read once, and then you have to close it. But if you have a use case requirement where you want to open a file and start reading sequential data continuously like a stream, then you can use proc underscore create underscore seq. We will talk about that in the future video. But now let's keep the simple version of it, which is proc create single. So I'll say proc create single of this, and I'll say jiffies proc show. This was actually version proc show, if you remember. I just changed version to jiffies, and this is what you see. This show function has this kind of prototype where you have a sequence file pointer as the first argument and a payload, which is not going to be used in our code right now. So the sequence file pointer, you can write to it. The sequence file pointer has a buffer. You're just supposed to write to the buffer. The easy way to write to the buffer is by using sequence printf or seq printf. You can see it's very similar to sprintf in a way, but it actually accesses the buffer from the sequence file pointer and lets you write to it. Here's where you can decide what is to be written. I'm just going to say jiffies equals %LLU because it's an unsigned long. So I'm just going to use this particular specifier, format specifier, followed by get underscore jiffies underscore 64. This is a function I'm going to be calling. And this function we just saw, it is defined in a file jiffies.h, right, which we saw in the other screen. So I'm going to just include jiffies.h in order to access this. All right. So we implemented the show function. But we also need to implement another function called proc jiffies cleanup that should let us unload this entry. That means remove this file entry from procfs when this module is getting unloaded. So in order to do that, I'm just going to say static void, use the exit macro here, the exit annotation. To know what is the role of init and exit annotation, look up my earlier video on loadable kernel modules on Linux. I cover that in depth in that place. You can just have a look into that. So let's say proc jiffies underscore cleanup. The prototype of it is void, and in here, how do I remove an entry in proc file system? Now here's where a new learning comes up. How do I learn new APIs? Let me tell you, on Linux kernel space, nothing is written permanently as an API that never changes, right? Linux kernel has always been evolving internally. So the APIs keep changing, they kept evolving. So in early days, you could use proc underscore remove, but now you should be using remove proc entry. How do I know that? I'll tell you. If you remember, I just showed you including procfs.h, which provides a procfs API. Look up the header file. You always learn this as a rule. The kernel source code is your documentation. The header files are your API guide. You look up the .h files to understand about any changes that have occurred in the Linux kernel, what new APIs are being provided. Just read the .h files, and then you can look up the source code of the kernel accordingly to find out the prototype information and how they work. So this is how you become a more efficient, or I'll say more proficient kernel developer, right? So if I just open up this file, include linux procfs.h. This header file defines everything that you want to know about procfs APIs. There's a proc operation structure. This was introduced in the recent versions of the kernel. I don't think this existed in the 3.x kernel. I think it came up at some time in the 4.x kernel, one of the versions, right? So there's a wrapper on top of file operations, by the way. And somewhere down the line, you'll find a lot of APIs in here. You can see proc underscore symboling, proc underscore mkdir, proc underscore mkdir mode. You can see a lot of files in here. I mean, a lot of APIs in here. Proc create single data, an interesting API here. And you can also see proc create data. There's also a macro called proc create single, which is a wrapper on top of proc create single data. And when you scroll all the way down, you'll also find entries like proc underscore create, which is a very low level API where you need to register your own callback handlers for open, read, write, close, which we don't do in this case in our module. When you scroll down a bit, you can see there's proc underscore remove, which is an old API, but now there's a modern one. I've seen this since the late 4.x kernel, right? Which is remove proc entry. Remove proc entry basically takes the name of that file, the first argument that you pass to proc create single, you pass the same entry, and under which folder. You can leave it to null to ensure it's in the top level directory. It's a void function, so you don't have to worry about the return value and all that. So you can just use this API in this case. You could just say remove proc entry of jiffies. And under which folder, I'll leave it as null. This argument is same as this. To know about all these parameters, what all parameters proc create single takes, because you see a function that takes about 1, 2, 3, 4 parameters. It can be very difficult to remember the arguments. Always look up the API again here. You just scroll up a bit. You can see this. Proc create single. The first argument is name, the mode bits, the parent directory, and the show function. It's pretty easy to remember, right? But if you want to know more details about it, you can also, if you see scope added. Just check. Yep. So if you see scope or any kind of source code navigation tool, you can hop right into it, right into the implementation to get more details. Looks like I think I should use not the definition but the implementation. So I need to say control backslash C, or sorry, I keep forgetting the C scope, help function symbol, right? So you can see, yeah, it's S. So you just use control backslash S. You can see the implementation in proc.c. It's here. Oh, it's a call. That's a call being made. Not in here. Scroll down a bit more. Looks like it's in here. Filesystems.c. Proc create single. File systems, no, not even this. Yeah, proc.c. Basically, you need to look up the procfs implementation. Right? So if you look up I think it should be in procfs core. If you go to fs proc core.c must have that particular implementation. Okay, not visible in here. Maybe I lost it, but anyways, just look at the implementation and find it out. Let's worry about that later. So coming back here, let's finish this. So here I'll just say remove proc entry of jiffies null and close this. If you're creating an out of tree module, you might also need to represent the module license. This is compulsory these days. I'm just going to use GPL. What other license can you use? Well, you can look up module.h header file. You can just look up include Linux module.h and search for module license in here, in this particular file. There's a nice comment. You can see this module license macro being defined. This is in the source code, include Linux module.h. So the module license, they tell you what license you can use, and this underscore license can be any one of these strings. If you want to make sure your module is GPL compatible, which it must be in this case, you use any of the GPL compatible license. I'm just going to use GPL. It's very straightforward. So GPL v2 license anyways. And if I'm going to make this module proprietary, you would use proprietary. And there are problems with it. You should not be using any kernel APIs if you make your module proprietary, right? If you're going to be distributing this module as a binary blob, making proprietary ensures that you have to make sure that you don't make calls to any procfs API, so which actually defeats the purpose. So I'm just going to use module license of GPL, and I'm going to use module author. All these are optional, so put a name here. I can just use name like this, and you can also use a module description to indicate what this module does. Just a good practice to have these both added. A simple loadable kernel module that demonstrates exposing a file under /proc file system. Okay, forgot a semicolon here. Let me add that. All right, I think we are pretty much done. We have implemented all that is needed. So let's save this file. And after saving this file, what I'm going to do now is to build this, you need a makefile. The makefile would be as simple as this. If you're building out of tree module, at a very basic level, the makefile would contain a obj-m colon equal to. It can be sometimes plus equal to, but colon equal to still works. And you can just type the name of the file, proc underscore jiffies, but put a .o.c here and save this. You can see that there's a file called procjiffies.c. So the makefile just contains build as object as a loadable kernel module. That's what obj-m actually means. Which one? procjiffies.o. This doesn't look like a complete makefile, isn't it? So if you just type make, it doesn't work. It says no targets, stop, and it says that because there's no make rules in here. There are no target rules in the GNU make. So basically, this makefile will be included by the cable systems makefile. So you need to build this module by using the cable system. Now here's an interesting trick. If you're using a distribution like Ubuntu or Debian, I feel many people's common use base is this. You might need to install all the necessary packages for kernel development, and those packages I've categorized in here. So I'll just do a cat. A quick disclaimer: I'm not a full-fledged Ubuntu user. I would say I'm as new to Ubuntu as you people. So basically, I'm more of an Arch and a Slackware Linux user. I've dabbled with Ubuntu as an end user mostly, but then recently I figured out we can do kernel development on Ubuntu with some extra effort. So here's what it is. If you're using something like Arch Linux or Slackware, I don't think you have all this complexity. All you need is to install the base level package, and that's enough. That'll take care of all the necessary libraries for even building the kernel. But if you're using Debian or Ubuntu, you might need to make sure that these packages are installed. So I've already installed these packages. You need Build Essential, which provides the compiler toolchain, make, and all other build tools. Need Flex, Bison, BC, it's a calculator, and CPIO, Dwarves, Gawk. All these are dependencies for the kernel build system. And yes, more importantly, you also need kernel headers for the currently running kernel. So I put $of -r to make sure that the module can be loaded for the current kernel. So I'm going to run the same command one more time. just to show you that all of these are actually installed. It's all installed in my system, so no problem at all. So make sure this package is installed, and after that, what you need to do is to build this particular module. You could just use make, let's say minus capital C. Let's change directory to /lib/modules $of uname -r. This basically is going to substitute with the currently running kernel's release number, right? /build. This will be a symbolic link to the kernel build folder, right? It's a stub skeletal build folder with all the make files required to satisfy the kernel build system. And then you could say m is equal to the current working directory. And then you can say modules. Again, the word modules might not be really required. It's a good suggestion to have it. Done. I do get a warning here, something like this, simply because I don't think I've installed the kernel debug package. So if you install debug package, this warning will not be there. This BTF generation is only required for kernel debugging. Otherwise, you don't have to worry about this. If all goes well, you will see module being created with a file procfs.ko. So when you look up this folder now, you will see a file called procfs.ko being created. You'll see a lot of intermediary files like the .o file. You can see procfs.o, procfs.mod.o created from a procfs.mod.c. This is a file that's generated by the cable system by analyzing the file procfs.c. So let's not worry about all these things, but ultimately what we really need is this particular module. Now, to test this module, before I test it, let me verify /proc. You'll see there are many files in here. You'll not see a file that starts off as jiffies. You can see that IRQ. After that, it starts off as KAllSims, right? There's no file starting with J. But after this module is being built, if I say sudo, I need to use insmod because the module is not installed. Uninstalled modules, you can only load them by using insmod command and the exact .ko file being passed as a parameter. So I say sudo insmod procfs.ko. This module is now loaded. If you don't see any errors, by the way, I have not used any kind of print functions in the kernel to print any logs. So if you run dmessage, you won't see any log being printed. These are the kernel logs. So nothing specific is printed in here. Looks like some unhandled key event in my ThinkPad ACPI module, but nothing else. Nothing else printed. Because I don't use any printk or PR notice or PR info kind of functions. But you can see in /proc, a new file is just now appeared called jiffies. Earlier this wasn't there, right? So if you just now to try to cat /proc jiffies, you can see it prints this value. In fact, what exactly happened when I say cat /proc jiffies, it ultimately invoked the function in the kernel, which is proc jiffies show, right? So you can see that file that is there. This function got invoked. What are the function writes to the buffer? The buffer just copied to user space. So every time cat command is executed, cat invokes read system call on a file that's open, that is /proc jiffies, and the reads callback handler will invoke this particular function ultimately. And what are the function writes to a buffer that's copied to user space, and user space just thinks that it got some data from some disk or storage, but in reality, you know what happened? The data got generated on the fly through this function, right? In fact, 99% of all the files that you see in /proc are implemented pretty much this way, right? They involve dynamically invoking some callback functions which gather statistical data dynamically from the kernel by reading a couple of variables or computing some data and then writing it to the sequence buffer that is copied to user space, right? So we can actually also verify certain interesting things. If you run a command like watch -n1, -n1 indicates run this every 1 second. What? cat /proc jiffies. Basically, it's going to execute. I'll not use watch command. When I use watch command, the problem is that I lose the old number. It's difficult to track down the old number. So instead of watch command, I'll use good old while loop. That's a while true. I'm using Z shell, so it prints this kind of a prompt. But if you're using bash, you get a secondary prompt which is colon. But never mind. I'll just say while true do, and I'll just use cat /proc /jiffies and sleep 1. This way, your output is printed and you can see the old number and the new number. You can actually do some math and find out the distance between it. Every 1 second, at what rate jiffies is incremented. So we can actually verify that by, I'll open up a new terminal. I think not this. Hang on a minute. Let me just, I'll bring up a new terminal. Okay. Let me keep this terminal aside and let me note down one of these numbers. Let me just, okay, I think I can stop it right here because we have enough numbers here, right? Enough sample data. I'll take this, last few digits is sufficient, 832 and 1083. So if we just do a echo dollar double parenthesis 1083 minus 832, you see a number comes up as 251. Okay, the next time I'm going to take the distance between 1334 and 1083. 1334 minus 1083, 51. And again look at 1585 1334. 1585 minus 1334, 51. If you do the math, the difference between each of these numbers will be in the order of 251, sometimes it'll be 252, sometimes it'll be 253. I've seen that happening. These are nothing but jitters, right? We call them jiffy jitters. And also it may be the fact that the cat command will take some time to run. There's some delays added by this loop. So it'll be 1 or 2 jiffies delay here and there. But roughly you'll see a number that's close to 250, right? 250 series. We can confirm something about this. The jiffies is now incremented at the rate of 250 every second. Every second it increases by the rate of 250. And now, how do you verify that? You can verify that by just going to this particular file. We can do a grep config underscore headset is equal to in slash boot slash config hyphen $of uname minus r. In many mainstream distributions like Ubuntu, Debian, and also Red Hat Linux, you'll find a file called /boot slash config, which is the kernel's build configuration. What is the configuration that is used to build the currently running kernel? You can get that details from here. From here, I'm looking for the config option called config headset. It's set 250. The timer chip is armed to raise an interrupt at the rate of 250 Hertz, which means the jiffies is updated at the rate of 250 times a second, right? So we can verify that. All right then, so what we learned in this small video is that we learned how easy it is to just look up the existing kernel source, adapt it to your needs. In this case, an example of interfacing something in /proc, right? So in this case, I've just exposed simple variable called jiffies, but you can also expose your own variables or your own data structure, or call some function which can compute some data and expose it to user space to your liking in your own drivers or any kernel subsystem that you build. Right? So if you have found this video useful, do comment on how you found it useful. If you're able to use it in your work anywhere, just let us know. Let me know so I can make more videos like this, which might be more useful to many of you kernel developers. Thank you very much. So hope to meet you in future video sessions. Thank you.